Let us try a more difficult example of a collision and conservation of momentum. So a van, mass equals 2,500 kg, travelling at 15 meters per second, rear ends a car, mass equals 1,500 kg, that is travelling at 10 meters per second. Okay, that seems okay. If the van slows to 12 meters per second, how fast is the car going? Going at the end. So what we mean here, okay, so we have a van, this is the before, and it's doing 15, and it hits a car that's doing 10. Boom. And hopefully you noted from experience that if one thing hits another, so it comes along, boom, and then they both move off. So they're both going to keep moving. So this is before, initial, final. This van is now doing 12 meters per second. So it's lost momentum. It was doing 15, it's now doing 12. That means this car has picked up some momentum and has actually picked up speed. It's got shunted forward. And we've got to find out how fast that is. And we can do this by doing a small thing. Let's do this. By conservation of momentum, P final equals P initial. This is cool. So we've got two vehicles. So P1 final plus P2 final equals P1 initial plus P2. So if we add up the initial momentums of each vehicle, add them together, they're going to equal the final momentum. Okay, so if we expand this out, because P, the momentum, equals mass times velocity, this is going to be mass 1. Because the mass isn't changing, we don't have to worry about final and initial. Velocity 1 final plus mass 2, velocity 2 final, equals mass 1, velocity 1 initial, plus mass 2, velocity 1 initial. And we know most of this information. We know the mass of the car. We know the initial velocity. We know this, we know this, we know this, we know this. Which one are we trying to figure out? We're trying to find out mass velocity 2. We know that, we know that, we know that. We know everything in there except for one piece of information. And if we know everything except one piece of information, we can solve it. So let's solve it. What we're going to do is we're going to stick in all of the numbers that we know. And this is the engineering way. When we do this, we're not going to worry about units. So this is going to be the van, I'm going to call 1. Car is 2, so mass of the van is 2,500 times the velocity of the van at the end slows down to 12 meters per second. Plus, we're looking at the moment, the mass of the car is 1,500 times, well, that's what we want to find out. Velocity final equals, well, what was the start values? Well, we had 2,500 times 15, that's the initial, plus 1,500, so it's meant to be 1,500, not 15,000, heavy car, 1,500 times 10 meters per second. That's how much it started. So we can actually run through this if we want. So that's 30,000 plus 1500 VF equals 37,500 plus 15,000. So we subtract 30,000 from each side. So 1500 VF equals 22,500. So VF equals 22,500 divided by 1500. By 1500 equals 15 meters per second. So the two cars collide. This one's travelling slower. This car, the van, when it hits, slows down. The car speeds up. Does that seem reasonable? The answer is yes. So what we can do with this type of problem, as I said, maybe we should put those around the other way. We go PF is equal to PI. We expand it out with all of the momentums, mass velocity, mass velocity, mass velocity, velocity. We stick in everything we know. We simplify down, rearrange for the unknown. Problem solved.